Okay, so this is the first of my 3 lectures on parallel programming. I thought what I'd do is to begin by telling you a little bit about who I am and what my background is. My name's Keshav Pingali. I'm a professor at UT Austin, and that's a nice picture of UT Austin, the campus. That's the campus tower, which is the center point of our campus. And some of you might be able to see this Colosseum-looking structure over there. For Zena's edification, that's not the Colosseum, that's a football stadium, which is actually bigger than the Colosseum. It holds 100,000 people. So we're crazy about football there. So I'm a professor in the computer science department and also in the ECE department. I also have a joint appointment with an institute there, which is called the Institute for Computational Engineering and Science, or ICES for short. And this is, as you might imagine, a lot of applied math people, computational scientists, and so on. We have one of the largest open machines in the world at the Texas Advanced Computing Center. So really, one of the advantages of being at Austin, at UT Austin, is that it's a hotbed of large-scale parallel computing. So that's what attracted me to UT Austin from Cornell, where I used to be before that. And then before that, I did my PhD at MIT with Professor Arvind, who's sitting over there. So Zena and I have a lot of things in common, and one of them is Arvind was our mutual advisor, although Zena is many decades younger than me. So back when I was working with Arvind, I used to do functional programming. And that's one of the many reasons I enjoyed Gabi's lecture this morning, because it brought back all those memories of functional language programming and Haskell and lambda calculus and all of those things. But I have to confess, I'm a fallen functional language programmer. So after I graduated, I said, I'm never going to do that stuff again. I'm out of here. I'm going to do something completely different. And so really all my work since I graduated has been with imperative languages. But I hope you'll forgive me anyway. So I'll try and relate what I do to your world. I think I remember enough about functional languages to be able to connect a little bit to your interests, but I hope you find what I say to be of some interest anyway. A little bit about my group. So I have a couple of research associates working in my group, and then about 8 or 9 PhD students. The numbers keep fluctuating. Unfortunately, every once in a while, one of them graduates, but I do my best to avoid that as far as I can. We also have visitors from many countries, and right now we have visitors from all of those countries there. So ICES has a lot of space for visitors, and there's also funding for visitors. So if you want to come and visit us, let me know. It's best not to come in summertime, although, I thought Oregon would be cooler, but it seems like it's about as warm as Austin is right now. But a good time to come is in the fall. That's our homepage. You can find all our code and papers, all of that sort of stuff. And we have funding from all of the usual places. Okay, so parallel computing. Back when I was a grad student many years ago, I was doing parallel computing. And of course, as a community, we've been doing parallel computing since maybe the late 60s, early 70s, and so on. And so since we've been working at it for about 50 years, you might be wondering, well, hasn't this problem been solved yet? Why are these guys still working on it? So the short answer is, well, we haven't solved the problem. And in fact, there are lots and lots of interesting research problems for PhD theses and so on for you guys. And that's because parallel computing, the platforms that we compute on, keep changing. And in addition, the applications that we want to parallelize also keep changing. And so one of the themes that I want to use in order to tie the different ideas in my talk together is to differentiate between what I'm going to call old world parallel computing and new world parallel computing. And by old world parallel computing, what I mean is the way parallel computing used to be, the issues that were relevant, that were important to parallel computing, even say about 20 years ago. These issues continue to be important, but meanwhile, there are many new concerns that have come up. So back even 20 years ago, parallel computing was done largely on dedicated clusters. So clusters like the one I was telling you about at the Texas Advanced Computing Center. So thousands and thousands of these computers connected up into a single dedicated cluster, and you get time over there, and you use those big computers. Of course, there are also big clusters at the national labs and so on. So all the computing was done on platforms that look like that. Another very important point is that the people who used those parallel platforms were small in number, and they were also highly trained scientists and engineers who didn't really mind spending maybe 10 years or so developing a code, maintaining a code, porting it from one generation of a platform to the next, and so on. So they were very good application scientists, and in addition, they took the time to learn things like MPI and parallel computing and so on and so forth, so they were also very good parallel programmers. And then finally, the kind of applications that people used to run on these kinds of platforms are from the computational science world. So by and large, there were things like finite differences, for example. So if you ever looked at finite differences, essentially the key data structures over there are all dense matrices, vectors, things like that. And so not surprisingly, there were lots of libraries, lots of parallel codes that were all concerned with vector computations, dense matrix computations. You've probably heard of the BLAS, basic linear algebra subroutines. Well, that's basically matrix multiplication, and then on top of that, they built matrix factorization, so LAPACK, and so on. Now, this world of traditional old-style parallel computing, of course, continues to be important, and a lot of my colleagues at ISIS that I was telling you about do this, and they do a wonderful job of it. But meanwhile, the world of parallel computing has grown tremendously, and it's grown tremendously because, first of all, we have many more platforms on which we want to do parallel computing. So all of your cell phones, right? Whenever I see the students on my campus, they're always walking like this, right? And that's because they're looking at their cell phones. If you look inside a cell phone, well, that's a parallel platform, right? So you have some usually ARM multi-cores in there, and then you have some GPUs, and so even your cell phones are parallel platforms. And of course, my laptop is a parallel platform. So we have many more parallel platforms on which to do this kind of computing. The new thing, again, is the cloud, right? So you can go to Amazon Web Services, and then you can run stuff over there. And so the barrier to entry for parallel computing has now become much less than it used to be. Parallel platforms are now ubiquitous. The other thing that's happened is now there are large numbers of people who want to use these ubiquitous parallel platforms. And most of them are not really interested in spending a decade or so building a code and maintaining it and so on and so forth. Rather, what they want to do is to implement something quickly to get it running very fast on some platform. And then, so things like time to market and so on and so forth become very important. And so it's a very different kind of crowd over here that now wants to use these parallel platforms. And then the final thing that has really changed, and changed in a very big way, is that the kind of data that we want to compute on is also very different. So instead of just computing on dense matrices and vectors and so on and so forth, a lot of the data that we want to compute on nowadays is unstructured and sparse, so large sparse graphs, for example. So all of you all of us do these web searches, Google, Bing, and so on and so forth. And as you probably know, there is a large graph that underlies that particular computation. So what is that graph called? I'm going to keep asking you guys questions because, first of all, that keeps you awake. And more importantly for me, that keeps me awake. So what is that graph called? It's called the web graph, right? So the web graph, basically the nodes in this graph are web pages. And then if there's a hyperlink from one web page to another one, there's an edge in that web graph. And then you do a computation that's called a PageRank computation on it. And so that was basically the foundation of Google. That's how those guys got started for ranking pages. So whether you know it or not, you're actually using these large, unstructured, sparse data sets. And so these sorts of computations have become very important. And so this world continues to be important, but meanwhile, there are many more new, interesting problems to look at. So this has led to what I'm going to call the search for scalable parallel programming models. And I put the word scalable within quotes because usually in this world, scalable means a program that runs faster if you give it more resources, like more memory or more computers, processors, whatever. Here I mean something quite different. By scalable, what I mean is something that looks like this, a programming environment that looks like this, where a small number of expert parallel programmers that I'm going to call Stephanies, so these are the expert parallel programmers, like the students in my group, for example, what they do is to build programming environments that basically hide the complexity of parallel hardware, these parallel platforms we would from these application programmers that we're going to call the Joe programmers, right? Sorry? The average Joe, yeah. It's an American thing, that's right. So it's the application programmers, they're domain experts, but they don't necessarily want to spend their lives understanding parallel hardware and becoming experts in parallel hardware because, as we were saying, time to market, things like that are very important for them. So the job of the Stephanies is to basically hide the complexity of all of this parallel hardware from the application programmers. Now, there's only one way that I know of to hide complexity, and that is through abstraction. So basically, the Stephanies of this world have to design abstractions that hide the complexity of the parallel hardware and enable these Joe programmers to do their job well. So that raises the question, well, what level of abstraction should we be implementing? So if we implement an abstraction layer that's very high level, very close to the Joe programmer, very close to the application level, then that's wonderful for the Joes because their job is simplified. On the other hand, it becomes very hard for the Stephanies often to implement those abstractions efficiently. And I know this is going to sound heretical, but functional languages, in my opinion, are one example of beautiful high-level abstractions which really do require a lot of effort to implement efficiently, and that's why that continues to be a research topic. In my world, there was a major effort in the 90s that was called High Performance Fortran that was led by Ken Kennedy at Rice. So he was one of the major players in our world. And HPF, again, was a step too far. Very high-level abstractions, very nice language, turned out to be very hard to implement efficiently, so nobody used high-performance Fortran. So that's the problem with making this abstraction level very high. If, on the other hand, the abstraction level is too low, right, it's easy for the Stephanies to implement these abstractions efficiently. However, it doesn't really simplify Joe's job very well, and so then perhaps that's not quite as useful. And so what we're looking for is a sort of a golden mean, right, an abstraction level that the Stephanies can implement efficiently so that the Joes do not feel that it's necessary to go to low-level programming, and at the same time, they can be implemented efficiently. So that's the tension that we need to resolve, the tension between programmability and productivity and performance. So the goal, again, to repeat, we want to support a large number of application programmers with a small number of expert parallel programmers and get performance comparable to hand-optimized code if you can, or close enough. Now, there's obviously no consensus about what these abstractions should be. But in my group, we've been doing something that we call data-centric abstractions for parallelism and locality. And we have implemented a system that we call the Galois system, and it runs on shared memory systems. It runs on GPUs, subset of it. We've just implemented on distributed memory machines. So we had a paper at PLDI a few weeks ago on that. And so it's based on a data-centric way of looking at algorithms that I'm going to call the operator formulation of algorithms. And it turns out the operator formulation is a way of looking at algorithms that's interesting even if you're not interested in parallelism. It's just a way of thinking about algorithms that we have found to be very useful. And that's the foundation of our work, and we've been doing this for roughly the last 10 years or so. So I just want to mention a few projects that are using Galois. So BAE Systems is using Galois in order to do intrusion detection in computer networks. So what they do over there is to build what are called hierarchical interaction graphs, and then they do data mining on these interaction graphs in order to quickly determine whether there is some kind of illegal activity going on within networks. So that's a DARPA project that's almost ended. HP Enterprises has used our system for designing enterprise systems, so workloads for evaluating enterprise systems. Circuits are basically large graphs, and so people in the EDA tools community have been using Galois on their own in order to implement FPGA routers and circuit design tools. So these are some of the papers that they've published. We work with people in Poland who implement finite element methods using our system. And so we've implemented a whole lot of what I think are fairly interesting algorithms on this system. And so this is just to tell you this is, relatively real, so to speak. And this is what I want to tell you about. So in this lecture, what I want to focus on are these data-centric abstractions. What is this operator formulation of algorithms, which is the foundation of our work? Now, the best way to understand what these data-centric abstractions are is to contrast it with the traditional way of thinking about parallelism. So if somebody comes to you and says, okay, you were in Oregon for 2 weeks and you had all these guys talking about parallelism in your sleep, and so while you were awake, what did you get out of it? Well, you might say, okay, I learned, for example, that if I have a map operation, so map F on some tuple with n elements, well, I can do all of those function evaluations in parallel, and so that's an example of parallelism, right? So what you've done over here is you've looked at this particular program or this expression over there, and you've extracted some idea about what can be done in parallel without really knowing anything very much about F. You didn't need to know that, right? Okay, now the same thing can be done in imperative languages as well. And in fact, in imperative languages, there's a large body of work which looks at programs and tries to extract parallelism from those programs. And one of the major success stories in that world is auto-vectorization. So as you probably know, all processors nowadays have short vectors. And so exploiting those short vectors, if you can do that, you get a tremendous boost in performance. On the other hand, extracting that vector parallelism is very painful. Well, that's done automatically by compilers like ICC, for example. And that's based on work that started 50 years ago at the University of Illinois, David Cook's group over there. So that's one of the success stories of this way of looking at parallelism. So for example, if I gave you this loop over there, and I said, so that's a for loop. I imagine all of you know what a for loop is, even if you're Haskell programmers. So the question is, well, is there parallelism there? Can those iterations be done in parallel? And what you'll probably do is you'll look at it and say, well, okay, X and Y, X is only being read. We'll assume there's no aliasing. So X is only being read, so it doesn't really matter. Well, Y is being both read and written. On the other hand, each iteration is only reading from, iteration I is reading from Y of I, computing something, and then updating Y of I. And so obviously all the iterations are writing into different locations. They're reading from different locations. So you can do the iterations in parallel. In fact, this is a well-known BLAS kernel, which is called, anybody recognize it? SAXP. Good. So it's scalar A times X plus Y. If it was double precision, it would be DAXP. Okay, so this is basically SAXP, and you can do the iterations in parallel. So you can examine the text of the program and say what can be done in parallel. But how about this code over here? In fact, this is just a map operation if you think about it. How about the second loop? Well, the second loop is more tricky because what you notice is the subscript here has changed. And in fact, each iteration is reading from a value from a location that was written to by the previous iteration. So this is actually a recurrence over there. And of course, you can parallelize recurrences and so on and so forth if you assume that the addition operation is associative, etc. So they probably talked about this earlier in the course. Okay. All right. So you can do it. However, if you don't know anything about plus, well, then you really have to do the iterations sequentially, right? So there's no parallelism there. How about this loop over there, the last one? No, 2i minus 1. It is? Okay. So what you notice over here is you're writing into the even locations of y, right? 2, 4, 6, etc., whereas you're reading from the odd ones. So actually, you can do that in parallel, right? So you have to look at the subscripts, you have to analyze these subscripts, and as I said, this is a body of work that's been going on for about 50 years. It's called loop analysis, and basically you look at the text of the program, this is what is important. This is the traditional way of thinking about parallelism. You look at the algorithm, like FFT. You see the butterfly, you know what can be done in parallel. You look at the text of the program, you can analyze these subscripts and so on. And there are very interesting, very nice dependence analysis techniques, as they're called, based on integer linear programming, which deduce very quickly exactly what is deduced, namely that can be done in parallel. Okay? All right, this is still old world programs in the sense that we're dealing with vectors, we're dealing with dense matrices, and so on. Here is what is called an irregular program. So you're dealing with some complex data structure like a mesh or a graph over there. So here is some pseudocode for it. And now suppose I asked you, well, what can you do in parallel there? Well, that's a little more difficult, but what you can see is, well, there's a loop over there, there's a while loop over there, so you can say, well, let's try and apply the same ideas over there. I'm going to look at the memory locations read and written by different iterations, and if they're all disjoint, well, then I can do them in parallel. That was the idea that worked so well in the old world case, so to speak. And in fact, over the years, people have developed static analysis techniques for analyzing programs like this, which are built out of these pointer-based data structures. So they're called points to and shape analysis techniques. Have you guys encountered those? You've heard the words? Okay, it doesn't really matter. They're interesting static analysis techniques, which are actually useful even for functional language programs. So it's worth knowing about them. And in fact, these are in many compilers as well, like LLVM and so on. Okay, so you can analyze the program in the same way that you analyzed the previous programs, programs in the previous slide. However, it turns out all of them basically come back and say, sorry, I can't find any parallelism because the locations that are being read and written might overlap, so there's no parallelism here. And so the question then is, well, is that because there's no parallelism in this program, or is it because we need better static analysis techniques? So, for example, your first guess was, oh, there's no parallelism in that last loop because you didn't do a refined enough analysis. But then you looked at it and said, oh, okay, yes, you can. Okay, so maybe we can have refined, better dependent. Okay, we don't really know, right? So this is essentially this old way of thinking about parallelism. This is what I'm going to call a computational-centric way of looking at parallelism. You're looking at the text of the program or the algorithm, and you're trying to figure out what can be done in parallel. Today in my group, we look at programs like that in a very different way. And we look at it in terms of what I'm going to call a data-centric way. So let me tell you first what that program does. So it does, what it implements, that pseudocode, is something that's called Delaunay mesh refinement. It's a very old algorithm that's used for guaranteed quality mesh generation. It's used in graphics. So we didn't invent this algorithm. The input to this algorithm is triangulation of some region. And again, the details are not terribly important. But what I want you to know is that in this triangulation, some of these triangles are badly shaped. according to some shape criteria, looking at the coordinates of each triangle. You can classify it either as a bad triangle, in which case we'll mark it as red. It's a bad triangle, it's flashing red, saying, somebody please come, remove my badness from me, right? So there are either bad triangles or there are triangles which are good and we don't really care about them. And what the algorithm does is a process of refinement. So you basically take each bad triangle and you do some operations on it in order to end up ultimately with a mesh without any badly shaped triangles, okay? And what I'm going to do is something that you're told you should never do, which is try and do a demo. So let me try and run a demo for you. No signal. Okay, patience. All right, so I think that's not going to work. So let me go back and I'll have to now use my hands in order, sorry? Okay, we're back. All right, so what I'm going to do is try and do that animation for you using my hands, all right? So look at me. All right, so as we said, the input is this mesh of triangles. Some of the triangles are bad. So what happens in this algorithm is you take a triangle and because it might be bad, for example, because it's very big. So we refine it. That's why it's called a refinement algorithm. So we split it into smaller triangles. But if we just do that, then it turns out it might violate certain invariants that must be preserved by all triangles. So what this algorithm actually does is it picks a bad triangle, then it finds a small region around it, which is called the cavity of that bad triangle, removes all of those all those triangles, and then replaces them with new triangles like I've shown over here. Okay? And some of these newly created triangles may themselves be bad, but that's okay. If you just keep doing this long enough, you can show ultimately you get a mesh without badly shaped triangles. Okay? That's what the algorithm does. And if I could have shown you that animation, well, you could have seen it actually running and refining it. But I've given you enough information, so now tell me, is there parallelism in this algorithm or not? Okay, you say yes, and the reason is, and the answer is yes. Okay, why? Yeah, because each of these refinements is affecting a small portion of this overall mesh. And so in a large mesh, at least initially, typically you have lots of bad triangles. And so what you can do is, as long as you pick triangles that are far enough from each other that their cavities don't overlap, you can obviously do them in parallel. If, however, their cavities overlap, you can do them in one order or the other, but you can't do them in parallel. So in a large mesh, there's actually lots of parallelism. And in fact, this particular code on our system scales to hundreds of cores. So what looked like, well, gee, I don't really know, there's a while loop over there, and I did some static analysis, and I don't know what. Okay, if you look at it this way, in terms of data structures, namely the mesh, and you look at it in these data-centric terms, then the answer is immediately obvious. This is the essence of what I want to convey to you. Okay? This is what we call the operator formulation of algorithms. So it's a way of thinking about algorithms where there are three concepts that I want you to remember. The first is an idea that's called an active element. Sometimes it's a node in a graph, sometimes it's an edge in a graph, here it's a triangle. Okay, it's some region in a big data structure where there's work to be done. And think of them as active elements as flashing red, saying, I'm bad, please, somebody come fix me, right? Okay, so those are active elements. The second idea that I want you to remember is this notion of an operator. What is an operator? Well, it's the computation that you do on an active element, right? So in this case, you basically compute the cavity of the active element you're working on, remove all those triangles, put new triangles back in. So you're updating the mesh, but it's a small region of the overall mesh. That's what the operator does. It's a local view of the algorithm, local to a single active element. Okay? And then the final thing that you need to know is this notion of a schedule or an order. In general, there are going to be lots of active elements. So what order should I do them in? Let's just take a sequential implementation. Well, I need to specify that. In this algorithm, it turns out it doesn't really matter. You can do them in any order at all. We call those unordered algorithms. But in other algorithms like discrete event simulation, if you've ever looked at it, basically there are events with timestamps, and you need to simulate what these events are doing in some network, but you need to do them in time order. So there, that's called an ordered algorithm, because there are active elements again, but each active element has a priority, so to speak, and you need to process them in that priority order. Okay, so those are called ordered algorithms. So I'll tell you more about the schedule as you need to see a few examples, but the schedule basically gives you the global view of the algorithm, right? The big picture. The operator is the local picture. And these are the only three concepts that you need to know in order to understand our way of thinking. The notion of active elements, sites in a data structure where there is work to be done. The notion of an operator, which is a small update that's made to the data structure. And then the schedule, which tells you the big picture, the order in which these updates should happen. Okay? And so for us, an algorithm is an operator plus a schedule. And as we said, once you look at it this way, it's immediately obvious that as long as these operators are operating on disjoint regions, there is a question of how you find such active elements that have disjoint neighborhoods, as we call them. We'll talk about that later. But basically, that tells you where the parallelism is. And then the only other thing that to note is that both the graph and there's a work list of bad triangles that you create. Both of them have to be parallel data structures. You're updating the graph. You can't afford to have a global lock on the whole thing, because then you've destroyed the whole point of it. So you need a parallel data structure that supports all of this. And so that gives you the motto that I have as the title of my talk, which is parallel program equals operator plus schedule plus parallel data structures. Okay? All right, so once we see a few more examples, I'll give you a connection to the standard von Neumann model of computing, which you have in imperative languages. So it turns out in our data-centric world, active elements are the equivalent of a program counter, right? Because program counter tells you which instruction to do. Here, the active element is telling you where there is work to be done. So that's the analogy you should have in mind. What is the operator in the standard imperative language? Well, it's a single assignment statement. It's an update to a state that's being made. Here, it's again an update, but it's a local update to this overall data structure. And what's the analog of a schedule in the standard imperative language model? How do you sequence all the assignments together? Flow of control. So the schedule is the data-centric analog of flow of control. So as you can see, these three constructs, which might seem a little strange over here, actually map very nicely into the traditional imperative model. This is also an imperative model, I'm afraid, right? Because it's based on updates to the state. However, it's a different way. It's a data-centric way of thinking about these programs. Okay, so this is just a cartoon that abstracts it out. I'm going to show you a bunch of algorithms just to tell you that it's not just weird algorithms like Delaunay mesh refinement that you can use this for. Even simple algorithms that you're all probably familiar with can be looked at this way. But basically, as I said, active nodes, edges, whatever. So sites where there is computation to be done. Operator, it's a local view of the algorithm. It's a computation that's done at an active node. And then the schedule gives you the global view of the algorithm. Now, I'm going to use a little bit of terminology that we have found to be useful in talking about algorithms. So we call it tau for the three dimensions along which we talk about algorithms. So there's the topology of the data structure. So for example, if it's a grid, well, then there's a lot of structure in that data structure, and you might be able to exploit properties of that in order to get efficient implementations. So the topology tells you something about the structure in the data structure, so to speak. The active nodes, the A dimension, basically where are the active nodes? So location and ordering. So in some algorithms, Delaunay mesh refinement is an example of what we call a data-driven algorithm, where there are just sites in the graph that become active on the fly. In other algorithms, you visit, for example, all the nodes in a graph and you do some computation in each round. So that's what we call a topology-driven algorithm. And then the operator itself could update the structure of the graph. That's what we call a morph operator. That's what our operator in Delaunay mesh refinement was. But in many graph analytics algorithms, for example, it only updates a label at a node. So it doesn't change the structure of the graph. It just updates labels. So we call that a label computation operator. So I'm going to use a little bit of this terminology as I go along because it's a convenient way of talking about algorithms. And it turns out that once you classify an algorithm along these dimensions, you can actually reuse a lot of the implementations for that particular class. Okay, so just to show you that you can analyze even simple algorithms this way, let's take single source shortest path. Do I need to explain what SSSP is? How many people know what SSSP is? Raise your hand if you do know it. Okay, so that's about half of you. All right, so let me just quickly go over the definition of the problem. So you're given, for example, this could be a roadmap of the US. So it's an undirected graph. The edges could represent cities. And we'll say that the labels on these edges represent driving distances or driving times, for example. So just some positive numbers that you have. One of these nodes is called the source, so A for Austin, for example. And what I want to know is, what is the shortest driving distance from A to every other node? Okay? So the shortest driving distance to B and C, well, that's obvious. It's 2 and 5, right? You can't do better than that. How about to D? Well, if I go through C, then that's 2 plus 1, which is 3. If I go through B, that's much longer. It's 12. So the shortest driving distance to D is 3. Right? So the goal of the SSSP, well, there are many algorithms for SSSP, but the goal is essentially, given a graph like this, you need to compute labels on every node that are the shortest driving distances. That's SSSP. Are we good? Okay, so for those of you who already knew SSSP, is this your SSSP also, or am I lying? Or okay, good. All right, so this is if you've taken an algorithms course, you know, this is one of the first problems that we are told. So GPS devices for driving distances. It's also used in social network analysis. They're called centrality metrics and so on. So it's a very simple problem. Okay, this is a problem. A problem could have many algorithms. The problem just says, this is the input, that's the output. Doesn't say how to compute that output. Okay, so what are some algorithms that you know for SSSP? Okay, everybody said Dijkstra, which is good. All right. Do you know any other algorithms? Bellmanford. Okay, that's another algorithm. Somebody said something I couldn't hear. That's for all paths, yeah. Okay, so you know Bellmanford and you know Dijkstra. Are there connections between them? Or are they, you know, in the standard way of presenting these in algorithms, right? Even in the best algorithms, but they just presented, well, they're just different algorithms. You know, Dijkstra woke up one day, invented this, so we call it Dijkstras Algorithm, and these other guys did this, and okay. So what I'm going to show you is, if you look at it in my terms, in data-centric terms, in terms of the operator formulation of algorithms, the similarity and differences actually emerge in a very nice way. Even if you don't really care about parallelism, this is a nice way of thinking about these algorithms. Okay, so there's a common structure to all of these algorithms. In fact, there are many more that algorithms that you probably have not heard of: chaotic relaxation, delta stepping, which is called a parallel algorithm, and so on. Well, there's a common structure, and that common structure is the way all these algorithms work. Every node is given a label, which we'll just call D for distance, and that's initialized to infinity, a large positive number initially, except at the source where it is 0. Okay? And then what is done is you basically, if in our data-centric terms, all of these algorithms use the same operator. Turns out the only difference between them is the schedule. Okay, and that's what I want to show you. So what is the operator that they all apply? It's called the relaxation operator. So the easiest way to understand the relaxation operator is to look at the starting state. So here you have infinity and infinity as the initial labels. This is at 0, so this is our active node, right? It's flashing red, saying some computation to be done. Now what can I do to B? Well, what you notice is if this guy's label is 0, and I add 5 to it, well, I get a number that's smaller than the current label, so actually I can lower B's label down. So that's called a relax edge operation. That's what this is. And usually what you do is you coming out of a node, so that's a relax node operation. And it turns out all of these algorithms, even the ones that people tell you are sequential algorithms, Dijkstra is usually presented as a sequential algorithm, delta stepping is a parallel, all of them use the same operator. This is the operator they all use. What is different are the schedules. So let's take a look at the simplest ones. So in fact, if I was writing an algorithms textbook, I wouldn't really start with Dijkstras algorithm. I would start with this one, because this turns out to be the simplest one. It's called chaotic relaxation. And here's the basic idea. As we said, initially, only the source node is active, so it's flashing red. And we're just going to put active nodes into a set, right? A work list, if you like. Okay, so that's our bad guy over there. So some thread will come, pick up A, and is going to apply the relaxation operation. So what's going to happen when I apply the relaxation operator at A? What is the update to the state? Whose labels get changed? Well, B and C. So B and C are now active. Anytime you lower the label of a node, it becomes active because now you need to look at its neighbors and so on. Okay, so I have B and C. Now I have a choice. Which one should I do next if I'm just doing it sequentially? In chaotic relaxation, you just pick a node at random. So that's why it's the simplest algorithm. So for example, I could pick B, and if I pick B, then I would relax D down to 12, so now C and D become active. So again, I pick one at random, I pick D, I have E and F. Okay, at this point I have C, E, and F, they're all active. Now when I pick up C, I can lower D down to 3. So now D becomes active once again. And so then I can pick up D again. Okay, so I just keep doing this, and you can show that if you do this long enough, as long as there are no negative weight cycles, this will converge and it'll give you the right answer. Okay? So what's the schedule over here? Pick an active node at random. That's the schedule. What's the operator? Well, it's specific to SSSP, that's relaxation. And the main inefficiency is that this can be exponential in the size of the graph because you're repeatedly relaxing these, you're relaxing along multiple paths repeatedly. And so this can be very, very inefficient. However, this is an unordered algorithm because you can do them in any order at all. And it's a data-driven algorithm because nodes are becoming active on the fly. Good? Okay, so let's roll our computation back to this point and say, well, is there a more intelligent choice that we could have made here? Instead of just picking a node at random, which is what chaotic, that's why it's chaotic, right? It's chaos guy. Is there a better way to do it? Well, there was a Dutch mathematician that told us a better way to do it. Pick the smallest one. Okay, so what's the intuition behind that? The smallest one will have reached its final value, right? It could not have, you can't lower its value anymore because I assume that all the weights, edge weights were positive. So in fact, that's what this other algorithm does. It's a different schedule. It's a different way of picking an active node from the work list. It also maintains a work list. However, when you want to go pick an active node to process, you always pick the smallest one. If a node becomes active, you put it into the work list. That could be anywhere in that work list. So what do we call work lists like that? There's a name for that data structure. It's what? I think the word is there. Yeah, it's a priority queue. So if you know Dijkstras algorithm, they make a big deal about, oh, we use a priority queue and that can be implemented using a heap and all of those. Okay, for us it's just another schedule, right? There are a bunch of active nodes. I want to pick the smallest one. That's it, right? Different schedule. So now you can see chaotic relaxation, Dijkstra. If you think about it, standard way, they look very different. Look at it this way, same operator, it's just the schedule that's different. And the schedules are implemented using a different data structure for the work list, namely a priority queue. And this is more efficient because we're always picking a node to relax, which will never be updated again. It'll never become active again as a result of future computations. Okay? And that's Dijkstra's algorithm. Okay, so the disadvantage of Dijkstra's algorithm is that if you want to do things in parallel, well then you can only do, I'm lying a little bit, but basically the only things that you can do in parallel are all the nodes that happen to have the smallest label. So if you have multiple nodes with the smallest label, you can do those in parallel, but usually there won't be much parallelism there. So that's why people call it a sequential algorithm. But in this way of looking at it, there's nothing particularly parallel or sequential about it. It's just what active nodes can I process, subject to the ordering constraints specified by the algorithm. Okay? All right, so is there an intermediate point? Can I sort of compromise between the extremes of chaotic relaxation, which has lots and lots of parallelism because I can do the nodes in any order at all, and Dijkstra's algorithm. So that's what delta stepping is. So in delta stepping, and I'll explain the idea quickly to you, basically what you do is your work list is now a sequence of bins, okay? And the way that you add an active node to a bin is basically all the active nodes with labels between, I'll just say 0 and delta are in the first bucket, delta and 2 delta in the second bucket, and so on. Okay? So when a node becomes active, you just add it to the appropriate bucket. If you want to go and pick something to work on, you always pick from the first bucket until it becomes empty, then you go to the next bucket, and so on. But within this bucket, if you have multiple nodes, you can do them in any order at all. So that's chaotic relaxation. The value of delta is something that you choose, that you tune. It's a tuning parameter for the algorithm. It depends upon whether you want to exploit parallelism or not, and it also depends upon the structure of the graph. I don't have time to go into all those details, but it's a tuning parameter. Given delta, you have a work list, and then again, it's just a different schedule in this way of thinking about it. So if I set delta to 1, you can see I get Dijkstra's algorithm, right? Because I'm going in order. If I set delta to infinity, I just get one big work list, one big bucket, and that's chaotic relaxation. And so I can trade off extra computation for parallelism by tuning the value of delta. Okay, and that's really delta stepping. Again, as far as we're concerned, it's just a different work list. And what we do in Galois, in our system, is we give you a bunch of work lists like this, which basically implement these different schedules. So if you want to pick stuff at random, we give you a set or a multi-set. You want to bucketize things, well, then we have a work list like this, and so on. So you pick your work list, you specify the operator, and then that's how you specify the algorithm. That's the data-centric way. Okay? All right. Yeah, okay, Bellmanford. All right, since you asked, we'll do Bellmanford as well. So what do you do in Bellmanford? Well, Bellmanford is what we call a topology-driven algorithm. So it's not data-driven where nodes become active on the fly and so on. Rather, you execute the algorithm in rounds. In each round, all nodes are active initially, and you just apply the operator at each node. And if any node becomes active again, if its label is lowered, well, then you do another round, and you just keep going. Okay? So it's a topology-driven algorithm. Again, the operator is exactly the same. It's just that the schedule that you're using is different. It's a topology-driven algorithm. What's simple about it is you don't need a work list because you just iterate over the whole graph, just working on each node at a time. Brute force, yes, that's right. But it's E times V. So it's topology-driven, and then each round is unordered. You can do them in any order at all. Okay? All right, so at this point, we can put them all together. So we have chaotic, Dijkstra, delta stepping, Bellmanford. And as I showed you, all of them use the same operator. Really, the only difference between them is the work list that you're using, the schedule that you're using is different, right? Same operator, different schedules. And now at this point, if you wanted to invent your own algorithm for SSSP, all you have to do is come up with some other crazy schedule, and then that algorithm will be named after you. Well, nobody cares because nobody really wants new algorithms for SSSP, but you can see, you know, there's nothing great or unique about Bellmanford, Dijkstra, these algorithms, right? They're just different schedules in this way of thinking about algorithms. Okay? All right, so the operator formulation brings out commonality and differences, and I think this is useful even if you don't really care that much about parallelism. So in this case, I showed you same operator, different schedules. So they all gave you algorithms that solve the same problem. But sometimes it's also interesting that you could have different operators with the same schedule. Right? And so an example of this, a few years ago, I have a colleague at UT, a very distinguished professor named Jaidev Mishra, who's actually a classmate of Arvind. So somehow my whole life is tied up one way or another through multiple levels of indirection to Arvind. So Jaidev is he's a member of the National Academy and all of those good things. He's also very well known for inventing a parallel algorithm for discrete event simulation. So remember discrete event simulation, you have events. Think of them as tokens that have timestamps on them, and you process them in time order. Okay? And when you process a token, it updates the state of some battlefield simulation or something like that. So it's big business, actually, discrete event simulation. And what Jaidev pointed out to me was, he said, one of the things that I realized a long time ago was that Dijkstra's algorithm is actually very much like discrete event simulation. But most people don't realize that. So how would you think about that? Well, if you think about it, both of them are ordered algorithms, totally ordered by some numbers. What is different is the operator. Right? In one case, it's a relaxation operator. For discrete event simulation, it's whatever update you're doing to that station where this token is there. Does that make sense? Okay. Now, Jaidev wasn't very impressed when I told him this, but, he's hard to impress. Okay. Now, we talked about, what time should I end? Plenty of time. Okay. All right. So far we've been looking at all of these irregular algorithms, as we call them in our community. So some large graphs, you're updating labels, you're updating the graph structure, and so on and so forth. So you might wonder, well, is this way of looking at algorithms, this data-centric way, thinking in terms of operators and schedules, is it useful for the simpler, more traditional algorithms? After all, we started with finite differences and matrices and so on and so forth. Well, actually, if you look at finite differences and you look at it this way, it turns out that if you talk to computational scientists, they already think in terms of operators. So I just want to show you very quickly what, so this is an example of a finite difference computation. So what you're doing, for example, is you have some region of space, and you have some initial conditions for the temperature in that space. And then what you want to do is you want to compute what the final temperature is going to be. Right? And maybe there are some heat sources in places. So you're solving the heat equation in some region. That's basically what you're doing. Okay? All right. And so if you use finite differences, what you do is you discretize your domain. And in this case, you discretize not using triangles. That's used for finite elements. Here, finite differences, so you use a regular grid, right? Like I've shown over there. So this holds the values of the temperature at different points in your domain at some time t. And then what you do is you basically compute a sequence of these temperature values. So the temperatures at the next time step, you compute this value over here by taking a weighted average of these 4 values. Okay? So that's called a 5-point stencil. And intuitively, if you think about heat, it's sort of diffusing, right? And this is basically simulating that diffusion. And you can actually start with the heat equation and use discretization, and you'll get some code that looks like this. That's called a stencil operator, right? And that's exactly how we think about it in our data-centric terms as well. If you thought in computation-centric terms, you'd have some loops like this, and it turns out that those dependence analysis techniques that we talked about, since these subscripts are simple enough, I minus 1, I plus 1, and so on, you can actually do the kind of analysis that we were doing earlier and find that you can actually do the I and the j loops in parallel. But in this data-centric way of thinking about it, this is what you do. You execute the algorithm in a bunch of rounds, and in each round you apply the operator to every point, and what you do basically is you compute using this stencil operation. So does this look like some other algorithm that we already looked at with a different operator? Okay, I'll leave that as a puzzle for you, and we'll come back.
Kind of match to finite, but it's
Okay, this will be a good question to take up at the end, all right? But this makes sense? You have an operator. What do different schedules correspond to? Just different orders of visiting these points. And different orders will give you different amounts of locality. So that is important for performance. But at this level of abstraction, it's unordered. You can do it in any order at all. Okay, so the last example that I want to pick for you, unless you have machine learning somewhere in your talk, people don't pay attention. And so we're going to do machine learning. All right. So I'm going to give you a machine learning example, which turns out, again, fits very naturally into this way of thinking. We talked a little bit about PageRank. I don't have time to go over PageRank for you, but I'm going to give you, show you a different problem, which is called a recommender system. And this is used to make recommendations to users in Netflix and so on and so forth. There are many algorithms for building recommender systems. In fact, there's an entire conference on recommender systems, believe it or not. It's actually probably bigger than POPL and PLDI combined. So, lots of people doing this stuff. I'll show you one algorithm for it. And so here is the abstraction of the problem, or specification of the problem. So I'm going to give you a database of users, some items, and the rankings that these users have given to some of those items. So for example, on Netflix, you watch some movies, maybe you've ranked those movies. So in this database, there are entries for every pair. So the pairs are you and the movie and the ranking that you gave it, and we'll do that for everyone. So that's the database that we have. And now the goal is to predict the ratings for items that the user has not yet ranked. And that's the essence of recommendation, because if I take all the movies that you have not seen, that you have not ranked, and I order them by the ranking, then I'll say, hey, you may be interested in watching these top ranked movies for you, but that would be a different recommendation for you, for example. Okay, so that's the goal. And work in this area really got triggered by the Netflix challenge, right, which some of you might have heard of. So back in 2006, Netflix issued this challenge. They gave an anonymized version of their database, a subset of it, and they offered $1 million prize to anybody who improved their internal algorithm by 10%. So anytime you have these sort of benchmark problems, right, everybody piles onto it. And, so that really gave a huge boost to this area. And just for completeness, the prize was finally won by something called Pragmatic Chaos from Bellcore in 2009. The algorithm I'm going to show you is different. It's not the prize-winning one, but as I told you, it triggered a lot of work on recommendation systems. And the algorithm that I'm going to tell you was invented by one of my colleagues at UT Austin, Indrajit Dhillon, and is based on something called matrix completion. So I'm going to give you a basic idea of how that algorithm works. So here's how I want you to think about the database. And it turns out it'll be useful for us to think about this database in two different ways. One, as a matrix. So in a matrix form, basically the way to think about your database is you have users as the rows, movies as the columns, and then if you have rated a particular movie, this user, that movie, then there's an entry over there. It's important to remember that if there's a missing entry, it's not zero. It's just a question mark. It's an unknown. That's what we're trying to estimate. Okay? That's the matrix view. It'll turn out to be useful to look at this matrix also as a graph, as a bipartite graph. All of you know bipartite graph? So basically you have users as nodes over here, and then movies, and the edges only connect over here. There are no edges between users or movies. That's why it's bipartite. Okay, and if this user has ranked that particular movie with some value v, well, I'm going to put a v on that particular edge. So it's a bipartite graph with labels on those edges. In the matrix view, what I'm trying to do is to estimate what those missing entries are. In the graph view, what am I trying to estimate? Missing edges, right? So what would that edge, value on that edge be? That's essentially what I'm trying to determine. Okay? Are we good? Okay, that's a recommendation problem. Now, at some level, this sounds like magic, right? I mean, it's like, well, you haven't yet watched this movie, and then I'm going to tell you, well, you're going to like it, right? So what's the essence of how can I guess? How can I estimate whether you're going to like a movie or not? Even though I don't know anything about you other than the movies that you watched and the rankings.
Statistical intuition. If we see the users that gave movie X high rating tend to give movie Y high rating, we can use this as a basis.
Very good.
There are measure of distance and do a regression, but that tends to be computationally unfeasible usually because it's
Okay, but the intuition you have is the right one, which is that even though we all like to think we're absolutely unique and nobody can predict what we're going to do and so on and so forth, the reality is in this room there are probably a bunch of people who think like me, maybe. I don't know. I mean, you guys are all Haskell guys, but you know.
I like space movies.
You like space movies. Okay, I like space movies too, all right? And perhaps we are roughly the same age and, you know, right? So, yeah, so, you know, that's the essence of it, right? So in other words, this matrix over here is what's called a low rank matrix. So in other words, you can think of it intuitively as there's a lot of redundancy in the rows because there are multiple users who have similar profiles, so to speak. Similarly, there are movies, space movies. Well, you know, if a space movie has been liked by a certain group of people, a different space movie is probably being liked also by the same group of people. So that's what's called a low-rank matrix. Low rank simply means essentially there's some redundancy in the rows, statistically speaking, and in the columns. And so the essence of what this algorithm does, that I'm going to tell you about, is it squeezes out that redundancy in order to get a sort of a normal form representation. I'm trying to relate to you guys, right? Normal form. All right. So here is the matrix completion idea. So this is our database, right, of users and recommendations. And what I'm going to do is I'm going to compute, now this is the matrix view. In the matrix view, I want to compute a matrix W and a matrix H such that W times H gives me, for every entry over here, it gives me roughly that value over there. So W and H are dense matrices. Keep that in mind. Now, how big are the rows and columns over here? Well, the number of rows, number of columns here have to be the same because of matrix multiplication. That's a parameter that you get to pick. But the idea is you squeeze the information into a thin, dense matrix and a thin, dense matrix, right? On the two sides. And then when you multiply them, the idea is for all the entries in here, the product, dot product of these two have to be roughly the same. Okay, if I give you W and H, now how do you make the recommendations? Just do matrix multiplication, right? So suppose this user has not seen that particular movie. Well, what would the rating be? Well, I take that particular column, this row, multiply, take the dot product. That's the estimate I get. So remember, W and H are dense, right? So I can multiply those two. What K is, that's called the size of the feature vector. You probably heard that term, feature vectors. So you get to pick how big it is. So intuitively, the smaller K is, the more information you're throwing away, so to speak. But then the larger K is, the more computationally intensive this becomes. But that's the basic idea. Okay, that's the matrix view. Now I want to show you the graph view. So in the graph view, here's what you're doing. Your database, again, is this bipartite graph with missing edges. And what I'm trying to do is, I'm basically trying to compute some vector labels over here. And the point of computing these vector labels for each one is, if I take the dot product of this little vector and that little vector, that should be roughly equal to the value there. Do you see the correspondence between this and this? Basically, all I'm doing is, I'm taking this feature vector W over there and just distributing it along each of the users, right? And similarly, this feature vector along each of the movies. So that's all. This and that are absolutely identical ways of looking at it. Does that make sense? Okay. So that's the goal. So what I'm given is this bipartite graph with missing edges but with labels over here, and I need to compute these labels on those nodes. And the constraint essentially is that if I take the dot product of these labels for every edge that's there, it should be roughly equal to that. That's the idea. Okay, so how are we going to do this? So here is where Dijkstras algorithm comes in. So this is an algorithm that's called stochastic gradient descent. There are multiple ways of doing this, but it's an iterative algorithm, and it's actually hard to believe it works, but it actually does. So basically what you do is you initialize these labels to some arbitrary values, and then what you do intuitively is you visit every edge in this graph. When I visit this edge, I take the current label here and the current label there, and I compute their dot product. Okay, if I have perfect information, what would the dot product be equal to? V. It would be equal to the label. So, that's exactly what I wanted. But usually you're not going to be that lucky, right? Usually there's going to be a residual. The residual is the difference between the label and the dot product. So what I'm going to do is I'm going to look at that residual, and then I'm going to adjust this label at that label so that when that adjustment is done, these two new values that I've computed over there, in fact, will be equal to V. Good. And then I go to the next edge, and then I do exactly the same thing, and so on. Now, of course, what you notice is when you go to the next edge, you're going to do some adjustment to 2 again, and then that means these two may no longer, the product may no longer be equal to V, of course. But you can show that as long as this data is reasonable and so on and so forth, if you iterate some number of times, then basically these labels will more or less converge. And then when these residuals become small enough, you stop, you have those two skinny matrices, and you can do any prediction that you want. Or in the graph where if I wanted to know user 2, what is the ranking he would give V, I just take the product of those two labels. Okay, but as far as the algorithm goes, I have a bipartite graph. There are labels on all of the nodes. I iterate over all the edges. Every time I come to an edge, I do some operation that adjusts these labels. And then I just keep iterating on them until some convergence is reached. Okay, so let's now see whether we can fit this into our way of thinking. This is obviously a data-centric view. I've told you the data structure, the updates. So what is the operator here? Well, the operator is basically whatever you're doing when you visit an edge. So you find the dot product of these two, you compute the residual, and then you update those two labels. So it's a local view, right? It's the adjustment that you're making when you visit an edge to the labels on the two nodes of that edge. That's the operator, okay? Now, how about the schedule? How would you classify this? Is it a topology-driven algorithm? Yeah, because we're doing it in rounds. In each round, I'm going to visit all the edges or all the nodes. That's another way of doing it. So it's a topology-driven algorithm, and it's got an operator of its own. And then I iterate until some level of convergence is reached. So does this remind you of a different algorithm that we studied? Well, it's like Bellmanford, essentially, right? So that's also a topology-driven algorithm. What we did in each round was unordered. So again, this is unordered in the sense you can visit the edges in any order at all. For Bellmanford, you're applying the relaxation operator. That's how you adjust the labels. Here, it's a different operator, but the schedule is the same.
What improves the previous iterations?
Yeah, that's right, until convergence. So again, you can see the structure. The nice thing about this operator formulation, as I told you, is it sort of reveals what is common and what is different. So if I look at Bellmanford and this, basically different operators, but the schedule is the same. For SSSP, we looked at all those algorithms, same operator, different schedules, right? So it's a way of thinking about algorithms that we have found to be very useful. It also makes manifest, essentially, where there is parallelism in these fairly complicated algorithms. Okay, so I'm out of time. So let me now wrap up with 2 slides that basically summarize what I told you. So here is the way that the abstraction that I want you to think about. So as we said earlier, basically in the standard imperative model of programming, you have an initial state, and then you do a sequence of state updates until you reach the final state. And then the execution of the program, one way of thinking about it is where, what, and when. So where should I perform the next computation? And in the standard model, that's given by the program counter. Program counter tells you what, where should you be computing next. What should I do at that point? Well, that's the assignment statement. So the assignment statement makes some small update, right? It reads to memory locations and it writes to a memory location. So that's a local update that's being made to the state. So that's the assignment statement. That's the local view. And then the global view, as we were saying, is given by the control flow that sequences these local updates so that you ultimately get to your final state. Right? So this is the standard imperative way of thinking about programs. And a long time ago, before most of you were born, John Backus, when he was awarded the Turing Award. You guys have heard of John Backus? Sorry? Fortran, yes. So he was given the Turing Award for two things that were mentioned. One is Fortran, and the other is he's the B in BNF, right? You know Backus-Naur form. So yeah, it's a way of describing the syntax of programming languages. So he's the B in BNF. So yeah, so he was, so he's a great guy. And his entire Turing Award lecture, he basically said, imperative languages are absolutely terrible for programming parallel computing because they force you to think in terms of what he called update at a time, right? Because he was thinking in these terms, there are assignment statements, and then you sequence these assignment statements, and if you want to do parallel programming, no, can't do it that way. So what he actually proposed was something you guys are going to love. He said you should use functional languages to program parallel computers, and he actually defined a functional language called FP. Right? And the semantics of FP was given by rewrite rules, and so you can apply the rewrite rules in different parts of your big expression, and you get parallelism. And there were even people who were actually building what they called a tree machine, which at the leaves you had the tokens of the FP program, and it executed in rounds. It parsed the program, and it found the redexes and applied the redexes all in hardware, right? And so back when I was, to tie things back, when I was a grad student at MIT, there's an exam that we were required to take where you had to read some papers and then present them. And the way Arvind operated is the same way that all professors do. Anytime you have a paper that you really don't want to read, you give it to some grad student and say, okay, this is your exam, you go read it. And so I had to read Margot's tree machine, and it was fairly impenetrable. And I think we did get the essence of it, and I reported it to Arvind. It was a success because obviously I passed the exam, right? So that was back then. That was John Backus's point of view. He said there's this one-on-one bottleneck, as he called it. Imperative languages can't be used. Imperative models should not be used for parallel programming because they're limited to word-at-a-time updates to the state, right? So, Backus was obviously a great guy, but I think he was actually wrong about this. And I think he's wrong because if I change my way of thinking about imperative models from that fine-grained point of view to this data-centric point of view. So instead of a program counter, if I think in data-centric terms, in terms of active nodes, that tells me where. Where should I be computing? If I think in terms of the operator, rather than single assignment statements, these are atomic updates that are made to the state, right? That is the operator. So instead of the assignment statement, my local view is given by an operator. And then the schedule is given not in terms of control flow constructs, but in terms of ordering constraints, if any, on the active nodes. Then I think this one-on-one bottleneck actually isn't there, in my opinion. And we've been able to implement, for example, that Delaunay mesh refinement program that I told you. In Galois, you can write it without any explicitly parallel programming, and we've scaled it to hundreds of cores on large-scale shared memory machines. Things like SSSP and so on, we execute on Stampede 2, which is our big machine, scales to 100,000 cores. So, I don't think imperative languages don't really have a bottleneck, this one-on-one bottleneck, as long as you change your point of view from this program-centric standard way of thinking about it, word at a time, to this operator formulation. Let me just wrap. Okay, that's my last slide. Zaina is looking anxious, but you have a question, so go ahead.
So your data-centric operator formulation algorithm seems like it applies just as well to functional languages and you've got graphic nodes or binary and so on.
Okay, I swear I didn't ask him to ask that question before my lecture, but you said exactly the right thing. That's the first thing on my last slide. Right there.
Yeah.
Right there. See? Beta reduction, right? So you can actually think about implementations of functional languages also in this data-centric terms, because if you say, what is beta reduction? Exactly as you pointed out, what are the active nodes? What's the term you guys use for it? Redexes, right? Yeah, redexes. So redexes, those are the active nodes when you do this way of computing. What is this? What is the operator? The operator is the beta reduction. That's an update, a local update that gets done. And what is the schedule? Well, different orders of processing your redexes. So you have normal order reduction and applicative order reduction, and what other forms are there? Okay, I'm fading out. This used to be, we used to worry about all of this stuff back in the day, but okay, those are just the schedules, right? Just different orders of processing your redexes. Those are schedules. So one way of looking at what I just told you is, I've taken what you already know, and I placed it in this more general context of other algorithms. But there is a very important difference, and that is, in this way of thinking about functional languages implementations, the operator is updating the program, right? You're rewriting the program. Whereas usually for these algorithms that we work with, you're actually updating the data structure state. You're not really updating the program. On the other hand, you're going to come back and tell me in functional languages, what's the difference? Programs are data. Okay, all right, very good. So we're all on the same page, but you can say, yeah, this is how you can relate what you already know to what I told you. Okay, and then, there are a bunch of things that one could connect this to if there was time. Zena, am I out of time? Oh, I have 10 minutes. All right. Okay, I have about 20 more slides then. All right. No, I don't want to stand between you and lunch, as I say. All right. So let me give you some more connections. So, if you look back, there's lots of work that you can tie in to this data-centric model. So, for example, transactional memory, right? So I don't know whether you guys are aware of the buzz about transactional memory, but for a long time, like maybe 10 years or so, it was a very big thing in the architecture community, right? So transactional memory, and people were building hardware transactional memories and software transactional memories and so on. Well, you can see these operators, what they're doing is transactional updates to the state, right? That's how a parallel implementation should happen. Each operator application should appear to happen instantaneously, right? And then the semantics of the program are respected. Does that make sense? So basically you can see how to use, if you had transactional memory, so if somebody built hardware transactional memory and it was efficient, well, you could use it for implementing some of these operators. Although what we have found is almost always these operators have some structure that you can exploit for efficiency. And so it's a sort of a CISC versus RISC kind of thing, Back when CISC instruction sets were popular, what they did was they took programming language constructs and implemented them essentially as single instructions. And then what Hennessy and Patterson and other people told us, right, was, no, that's not a good way of doing it. We should give you these small instructions out of which the compiler can build up implementations, and that's much more efficient, right? And so that's essentially my opinion of transactional memory. I think it's an interesting idea, but it's like CISC. It's a way of thinking that says, take constructs in your programming model and implement them directly in hardware. Perhaps that's not the best thing to be doing, right? Another thing that I'd like to connect to is a programming model that's called Unity that was actually developed at UT Austin a long time ago by Mani Chandy and Jaydev Mishra. So in Unity, they have this notion of atomic state updates also. On the other hand, they don't really have any notion of schedules, because for them, all their algorithms were unordered, and they just had fair scheduling, right? So as long as no active node was sort of ignored permanently, it was fine. They didn't really care, right? And so in Unity, the notion of these atomic updates, which we call operators, right? They're there. On the other hand, they didn't go as far as adding in the schedules. And then once you add in the schedules, then you can see that the way they have a whole book, a very nicely written book on Unity, but then they say, well, this is how you would do single source shortest path in Unity, right? Because you're forcing a particular schedule, and then you're restricted to a particular algorithm there. since we have the flexibility of choosing schedules, for us it's not like, well, this is how you do SSSP in the operator formulation. In fact, what I showed you was you can take all the algorithms for SSSP and analyze them in terms of the operator formulation. So I think there's a richer way of thinking, but again, you can see some roots back in this very nice work by Mani Chandy and Mishra, which really deserves to be known better in the programming languages, in the parallel programming community than it is. Stencil programs, so halide. So these are basically ways of, these are domain-specific languages for finite differences. You specify the stencil, compiler does the rest. It builds a parallel program for you, right? So in our way of thinking, basically, it's an unordered algorithm. I give you the operator, and then you give me the implementation. So this is an idea that's very old. So Guy Steele, who's one of the major guys in functional languages and so on. So he implemented a stencil compiler back when he was with Thinking Machines. And then more recently, this idea has been rediscovered by Saman Amarasinghe at MIT. So he has a DSL called Halide, which they use for image processing, and Adobe has picked it up. And so it's a success story for DSLs. On the other hand, both Halide and these stencil programs are only for these mesh program, very regular programs, finite difference stencils. So it's not as general as our way of doing it. And then there are other things like vertex programs, so GraphLab and Guy Blalock's Ligra and so on. So there, again, the operators are restricted to just looking at nearest neighbors. They can't do updates to the graph structure and so on and so forth. But again, this is a special case of our operator formulation. So if you look hard enough, you can see connections to everything from lambda calculus to all of this work on stencil programs and Unity. Okay, so what I want to do next week in the 2 lectures that I have to give is to show you how to think in terms of implementing this model. This was a programming model. It's a way of thinking about algorithms. It's a way of writing algorithms, if you like. We've implemented it in C++. You can implement it in any other language also, imperative language. But yeah. So how do you implement it on shared memory machines? How do you implement it on distributed memory machines? So what Zena told me is that I should not assume that you know pthreads and MPI and things like that. So what I'm going to do is include some material on that so that you can, connect what I told you today to actual implementations. And with that, let me stop. There are a few minutes for questions. Or are we ready for lunch? You have a question. Yes?
If you have 2 active triangles and they're like overlapping, you have to process them.
Yes.
You can't process them in parallel.
Mm-hmm.
Do you think about these like conflicts as being included in the schedule, or is it something about?
No, it's in the implementation. The schedule just says they're unordered, do them in any way you like.
And there's some other thing that stops the schedule.
Exactly, very good. That's exactly the right question to ask. That's what I'm going to talk more about next week. But I'll tell you the intuitive idea. So the intuitive idea is what we do is the conflicts are handled by our runtime system. Okay, and what the runtime system does is there's a thread, it picks up a bad triangle, another thread picks up another bad triangle. Now, how does it actually do the operator? What it does is it first computes the cavity of this bad triangle. So there are just a bunch of triangles around it. You don't know exactly how big that cavity is going to be. So you can't, basically every triangle has a lock associated with it. It's not really a lock, it's more like a mark. How much do you know about parallel programming? Okay, so I'll talk more about it, but you can think of this essentially as, imagine that there's a token on every triangle, okay, just abstractly speaking. And what I'm going to do when I build my cavity is, whenever I want to include a triangle in this cavity, I take the token. And that taking of the token is done atomically, right? So that has to be an atomic instruction, because you can't have 2 threads both grabbing that token at the same time. So that's where we use atomic instructions. But basically the idea is, I keep around set, I'm the thread working on a bad triangle. As I compute the cavity, I keep taking the tokens. And if I have all the tokens for my cavity, then I just go ahead, I do the update, and we're done. If, on the other hand, when I get to a triangle, and I find its token is already gone, then what I do is I roll back. And the rollback is done essentially by taking all of the tokens that I currently have and putting them back, right? And then I try. Sorry?
So it kind of lives in the operator and it's kind of
It lives in the runtime system. The handling of conflicts is done by the runtime system. And the cartoon picture you should have is there's a token sitting on every triangle. You have to acquire all those tokens before you can do your update. Okay? And then, so that gives you the atomicity that you need for operator execution. But then there are other problems, like it's called live lock. So live lock basically, there are two threads both trying to do some work. You detect the conflict, I detect the conflict. Yeah, so I roll back, you roll back, and then we both try again, right? So it's like this Ethernet problem, if you know how Ethernet works, right? There's a bus, two guys are trying to transmit at the same time. So how is that resolved? Well, basically there is exponential back off and so on. So we tried that. That doesn't work quite as well as our current system. Our current system, basically what it does is, if you basically looks like you have live lock, then you sequentialize the execution of those two guys on the same thread. So they just get done one at a time. So that's the long answer, but that make sense?
Yeah.
Okay. So it's handled in the runtime system, not in the operator. Because the operator is specified by Joe. And Joe doesn't really want to know anything about live locks, deadlocks, all of that stuff, right? So we give you a data structure library that has these tokens in them and so on and so forth. So that's one limitation of our system. You have to use our data structure library in order to implement your algorithm. Now, on the other hand, we give you some primitives so that if you know what you're doing, you have to be a Joe++, but if you know what you're doing, you can build your own data structures that are consistent with our execution model and so on. Now, the other thing that I want to emphasize is that the operator formulation, the way I've described it, it looks like all of this conflict detection and so on has to be done at runtime, but that's just for these really complicated algorithms like this mesh. But for stencil codes, right? We talked about how to think about that also in terms of the operator formulation. And you can see for a stencil code, you can actually look at the operator and the structure. At compile time, you can say, I don't need all these tokens and all this jazz because really I can do everything in parallel, right? There are no conflicts over there. Now, in our system, that sort of thing, because there are enough people working on finite differences and stencils and so on and so forth. So what we focused on are these fairly complicated graph algorithms, like these algorithms that I told you about. But there's nothing in this description, right, of operator formulation or the way we think about it that prevents you from extending our system to include some compile time analysis and say, okay, I don't need all your tokens and so on. And in fact, you can write Galois programs in our C++ implementation where you can turn off all the conflict checking if you know what you're doing. So I know I don't need conflict checking here. Okay. So there is our implementation as it exists, and then there is what the abstract model actually lets you do. And those are different things. Okay, any more questions? Yes?
This is like stupid, but I really get confused about updating and state when you say we're functional. So I associate that with more immutable kind of way of thinking. But then we're up to, so I mean,
You're going back to that lambda calculus.
Well, right, so from a, that's a good way to phrase it, is does a beta reduction, have to overwrite something that was in its place previously, right? Is a step sort of like a rewriting in some way?
What do you think? You made the analogy, so help me.
So in a pure functional version, you can say it one step takes a lambda expression and produces a new lambda expression, which can then be optimized if you don't care about the old one to happen in place.
Exactly. I think you said it a lot better than I could have said it, but yeah, there was a time when I used to say things like that, right? It was back in my functional languages days before I fell from grace.
So that makes sense, but where are we doing here? Like,
What are you doing here? Okay, I was afraid some of you would ask that question at the end of my lecture. You know, what the hell am I doing here in this lecture?
no, like, where do we sort of stand? Because I guess it's like it's implementation detail that we don't want to think about. We want to try not to think about some of those details, but like it's an optimizing thing that's going to distract us if we.
So, as I understood it, the operator here is usually an imperative operator that changes memory.
Yes.
Overrides things. And so, in this model, in a pure functional language, we're working in the imperative language.
Yeah.
And that's where we start.
So how do you think about rewriting? I'm asking a philosophical question at some level, but you know, I give you a lambda expression, right? And I want to rewrite it. Do you think in terms of producing a totally new lambda guy and I don't care about the old one and so, right? Or do you just think in terms of I just update it in place? I don't know. I think in terms of just updating in place, right? A rewrite, right?
Does this speak to the gap between parallel and concurrent? If that's useful or meaningful here? It sounds like we're much more on the concurrent side, fundamentally. I mean, based on, I guess, at least on definitions that like we had in the previous lectures.
Okay, I should have attended those previous lectures, but I didn't. But you know,
This thing, like it was defined for us that like parallel is the deterministic version, concurrence the non-deterministic version.
okay, I'm not sure I would agree with that,
Well, it
but
sounds like what we're
yeah.
doing is like we're going, we're not like 100% safe on race condition.
No. We are completely safe when it comes to race conditions. But in some algorithms, in fact, many algorithms, you have what's called don't care non-determinism, right? And you can see that in lambda calculus, right? If I have a bunch of redexes, you know you can rewrite them in any order at all. And you have that, what's your theorem called? Church-Rosser theorem. Okay, come on, Church-Rosser theorem, right? So what does the Church-Rosser theorem tell you? It says you can do things in many different orders, but ultimately you'll reach the same answer, right? So that's there in all these algorithms as well. SSSP, you know, there's this implementation non-determinism. I can pick any active node. If I'm doing chaotic relaxation, ultimately I end up with the right answer, right? Okay, I think people are getting hungry, so why don't we stop here, and I'll be happy to answer questions.